The next speaker I would like to introduce is Gerasimos Angelatos from the Tureci lab, also at Princeton Electrical Engineering, and he will talk about a reservoir computing approach in quantum state measurement.
Hi everyone, can you guys hear me? Okay, great. Thanks first I'd like to thank Bert for putting this presentation together so sort of last minute. As he had said, I'm going to sort of present our work constructing a framework to do reservoir computing for quantum state measurement. And I've done this along with Saeed, who, weird, I have a clicker. Okay, great. This is done along with Saeed, who you just heard from, and our advisor, Hakan. First, I'm going to sort of, go through a bit of background on what reservoir computing is and our proposed in-fridge physical reservoir computer, and then discuss its measured performance on a quantum measurement task. So reservoir computing, generically, is a machine learning framework designed to process time-dependent signals. You can think of it as a generalized recurrent neural network. So in reservoir computing, you have some dynamical input signal, which is fed into some general reservoir, which is some large, complex, and sort of high dimension, or sufficiently high dimensional system, and it's going to, under the influence of this input, evolve to some non-trivial state in its phase space, and the sort of output of our computation is done by just taking a linear combination of these nodes, or sort of dynamical variables. And the power behind reservoir computing is that we're not really interested in optimizing the internal structure of our reservoir. Instead, the only thing that's sort of trained is how this linear combination is taken. So training becomes this convex, easy task, which is unlike what you have in recurrent neural networks. And some applications that people have used reservoir computing are modeling and forecasting. And in this talk, I'm going to specify on time-dependent classification. This is an example of a memristor array-based reservoir computer, which is being used to classify the digit 2, which is being read in, and it realizes that that digit was indeed 2. So there's, as you mentioned, that there's sort of two main sort of approaches for reservoir computing. Like most sort of machine learning frameworks, there's a software-based approach where there isn't an actual physical reservoir computer. Instead, your structure lives in software, and it's basically an algorithm where your nodes follow some update rule where their state depends on the input and the sort of internal, like, previous history of the entire network in some nonlinear fashion. And sort of two main frameworks for this are either echo state networks or liquid state machines, if you're perusing the literature. But in this talk, I'm going to describe a proposed sort of physical hardware-based reservoir computer where we're envisioning a reservoir that's an actual dynamical system, which is then going to follow some set of ordinary differential equations, which we can sort of solve. And the sort of advantage of these approaches is that this allows you to do this sort of computationally intensive reservoir evolution in real time. In addition to those memristors that I showed here, people constructed these things using FPGAs, photonic delay networks, spin torque arrays, and I've even read a paper about using a bucket of water as a reservoir computer. And if you're interested in a review of sort of reservoir computing, I would recommend this paper. But all these approaches that I've talked about to this point have looked at reservoir computing applied to classical signals. However, we're sort of interested in how a reservoir computer developing a framework for how a reservoir computer could process a quantum system signal, which is, is going to have some significant conceptual differences. So, I mean, for the experiments in the audience, this is going to be relatively hand-wavy here, but in general, right, we're going to take some signal out of the quantum system that we're interested in measuring, take it out of the fridge, and feed it into some external electronics, which are going to do some, filtering and just general processing. And in a reservoir computing approach, if we instead feed this signal directly into some physical reservoir computer, we're able to move a lot of this processing back into the fridge. And this is the sort of structure we're envisioning, where this reservoir computer is going to act as an analog processor on this sort of quantum signal. And I'd like to point out that this sort of echoes these quantum classical algorithms that we're starting to see in sort of quantum information, stuff like QAOA, where we're doing this sort of computationally intensive dynamics in hardware in real time in the fridge. And then this training, which is, again, as stressed before, is this linear convex problem, is done basically in software. So you're getting the best of both worlds there. And sort of for our friends in this session, we're going to consider a superconducting quantum system and that we're going to try to measure. So it would make sense to construct a reservoir also out of a superconducting circuit. And in particular, system I'm envisioning as this sort of abstract reservoir here is going to be this sort of Kerr oscillator network where we have some nonlinearity and some hopping, and it's going to be driven by the signal from our quantum system. And you can sort of solve for the differential equations for the node field amplitudes in terms of this framework, which is probably more familiar to machine learning and reservoir computing people. And basically the thing that we're going to read out is the x quadrature of each of these oscillators. The only thing that I have left to describe, I guess, is the sort of system that we're going to try to measure. So I'm envisioning sort of multi-qubit readout set up here, where you have a set of qubits dispersively coupled to a readout cavity D. And when we're doing readout, we're going to turn on this drive, and that's going to populate this readout cavity. And that signal is going to be transmitted to the reservoir computer. And the field that exiting this cavity depends, because of this dispersive coupling, on the sort of total inversion of our qubit system. And so from this, you're able to learn about the qubit state. And in fact, this sort of setup allows you to do full tomography with just this signal. The measurement task in particular is going to consist of, okay, we're going to initialize, we're going to construct some training data by initializing in some known state in our measurement basis. So like Z1, Z2, blah, 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 blah. And record the field coming out of the reservoir, or out of the quantum system. And we're going to do this numerically by solving a stochastic master equation, and also include qubit decay and cross-coupling in sort of realistic parameters here. And that's going to form our training set, which we're going to train both a reservoir computer and a sort of match filter, which is the traditional sort of signal processing way of performing quantum measurement. And we're going to specialize in the case of 2 qubits, because that's already enough to do a non-trivial classification task. So yeah, the reservoir computer we're considering is, again, a Kerr network, as I said earlier, consisting of only 5 nodes. Because and its sort of internal parameters, which aren't optimized, are going to be random, and I've chosen realistic parameters here. And we're going to train it on sort of 100 different measurement traces, one of which is sort of shown here, corresponding to this is corresponding to the qubit being in state 1-1 initially. You get this noisy field coming out of your system, and that's going to drive the reservoir to some sort of interesting state. Here, these are the 5 nodes. And we've trained it to return the probability that the initial qubit state was in some state. So there's 4 different possible initial states. And indeed, you see that it does, the probability of the qubit being in 1-1 does rise to 1 relatively quickly, so the reservoir is classified the state. I'd like to sort of contrast this with the traditional sort of matched filter approach, where you use the same training set to construct an optimal linear filter and a set of corresponding bins where we expect the filtered signal to fall into. And then you filter the signal coming out of the reservoir of the quantum system, and you classify based on which bin it falls in. So this is the matched filter approach to the same signal. If we want to sort of to quantify the performance of our reservoir computer, I'm going to construct this thing called a classification fidelity, which is just as a function of time looking at how many, the fraction of a test set that the reservoir computer has classified correctly. And this time starts when that sort of coherent drive on the readout cavity turns on. And you can see that the reservoir computer, I think it's 2,000 samples, does reasonably well. It has a peak of around 95%. And then it sort of is limited by that decay of the qubit and sort of crosstalk, which causes you to lose that initial state information at longer times. And you can compare this performance with how a sort of matched filter, which is again the optimal linear filter for this problem, performs, and you see that they're pretty comparable. This is match filter with the same training set, and in the lighter color is a ideal, like infinite training set match filter. But where the reservoir computer sort of really shines is that its performance is basically unaffected by the size of your training set. It's able to learn the classification task really quickly, whereas it takes, you know, a sort of multiple orders of magnitude larger training set for the match filter's performance to start to match that. And so this could be useful for performing rapid calibration, where you need to only, you know, initialize and retrain, like with a couple samples, and then your reservoir computer will be good to go. Another sort of power behind this reservoir computing approach is that it's really model independent. It doesn't matter what that quantum system that I'm interested in classifying is. So I can replace that dispersive readout Hamiltonian with this sort of full James-Cummings Hamiltonian, where now, you know, our sort of measurement basis isn't conserved by this James-Cummings interaction, and that's going to cause the qubits to decay as they're being measured, as they show here in this light color. And so the reservoir computer, which initially had read out the initial state after the qubit decays, eventually decides that it's now in this new state that it had been in. But that's still a loss of this initial state information. However, if you look at this classification fidelity, we'll see that the reservoir computer is still doing quite well. And yeah, this cutoff is again because of that loss of initial state information before. And we don't have to just measure states in this sort of measurement basis. We can use a reservoir computer trained in this measurement basis, so that same training set we've gone through earlier, to measure sort of arbitrary quantum states. So here's an example of 0, 0 plus 1, 1 being fed into the reservoir computer, and because of this interaction that's with the computer, it quickly causes the quantum state to collapse to 1, 1 in this case, and the reservoir computer learns that. Now the statistics of the reservoir computer, if you do these repeated measurements, are going to agree with those of the underlying quantum system. So this basically allows you to do tomography, and for full tomography, all you need to do is single qubit rotations before you start measuring. But yeah, so you can do repeated measurements of sort of, here I've done for 3 different states, and you see that basically there's a 96% fidelity of what the reservoir computer says you are versus what the underlying quantum state actually is. And sort of as a final point, I'd like to stress again that there's no sort of internal optimization of these reservoir parameters being done here. So here's 5 different random 5-node reservoirs, and they all have a reasonable classification fidelity. And as you increase the node number, this sort of variance is going to decrease, and they're all going to converge to that optimal performance, and that's because you can find like a sort of sub-network that does well. And with that, I'd like to thank you guys for listening, and just sort of summarize that we've sort of developed this like framework for reservoir processing of quantum signals, and I've shown that you can sort of, or proposed that you can have a sort of hardware efficient analog processor in the fridge, which is this reservoir computer, and this, in this case, that it was ideally suited for real-time quantum state measurement. We can extend this to doing tomography or continuous monitoring of some quantum system, and this is all very generalizable to, you know, whatever system you're interested in studying and however we want to do this measurement, and we're even whatever we want to make this reservoir computer out of. Okay, guys, thanks for your time. I'm going to take any questions.
Thank you, Gary, for this very interesting talk. Are there any questions by our quantum community here? Or maybe I can start with one. So to understand correctly, that basically this will provide us, you know, a significant amount of speed up of, you know, tomography and readout of the qubit, or like many qubit states, compared to maybe nowadays FPGA-based techniques that is external to the fridge. Is that right? So do you have an estimate of like how much of the advantage this would be?
So this is all like a theoretical proposal,
yeah.
And obviously I'm not comparing with FPGAs like outside of the fridge, but yeah, the idea is that this computation is done in real time. So, you know, this is the readout time. This is in terms of that time when the drive is turned on.
So basically on the gate time, basically.
Yeah, exactly. Okay. And well, so for this tomography, this was 400 initializations and then measurements to measure this. So you need to still, as you do with normal tomography too.
Yeah, right? It's the averaging.
Yeah.